Well, hello everybody. Here in this video is where people normally begin when they learn Calculus 1. And by that, I mean that the first topic that they normally learn about is a limit, okay? So this video, naturally, I tell you how you understand limits. All right, now, limits are complicated and there's various levels that I can explain it at. But in this video, for the most part, I'll try to keep it to the simplest end of the explanation. And in other videos, maybe we'll go a little bit deeper into it. But for now, hopefully, try to keep it simple. So, in order to get your mind ready for this, I need you to think about something first. Okay? So, you think about this first, and you just let it sink in, and then I'll add some things to it as we go along. So here's a function that is more or less random. I'm just using it for the sake of example here. And I want you to notice about that function that when you put 9 in, you don't get an answer back out. Another way of saying that might be that f of 9 is undefined. Okay? All right. Well, why is that? Well, okay, so put 9 in for x. 9 minus 9 on top, that's 0. That's no big deal. Root 9 is 3, and 3 minus 3 is 0. In the denominator, well, that's a problem. There's no answer to 0 divided by 0. Okay? So, all right, I've made my point. F of 9 is undefined. But, let's go a little bit further than that. Does the function behave in any predictable way when x is very close to 9? So let's say that 9's no good. Is there any predictable behavior when the x is very close to 9? Like, 8.99 or 9.01, that sort of thing, okay? So that's the question that we'll end up exploring here right now. All right, so what I did from there is I thought, well, let's make a table and see if there's a pattern to the table. And I think the way I made the table shouldn't surprise you. I've made the table in a way that the x gets closer and closer and closer to 9 from both sides, all right? We can probably agree that that's what's happening with the x. And then I just did the calculations for y. That's what a function is, isn't it? In a function, x is the input, you do the math, whatever it is, and then y is the output. Okay, so I'm trying to see, how does the x influence the y? I did the calculations. Do you see a pattern? I hope you see a pattern. I hope that you don't think those numbers look random. Do you? They definitely don't look random. It appears that the closer x is to 9, then the closer the y will be to 6. Look at it, 5.8, 5.9, 5.99, and then I'm pushing to 9 on the other side. For the x, I get 6.1, 6.03, 6.007. Yes, I think we can agree that that's what's happening. All right? Now, we could stop right there and say, all right, we see the pattern. We agree what's going on. But the math is full of notation to express ideas and concepts. So what we say about that is this. We say for that function f of x up there, the limit as x approaches 9 of f of x is 6. Okay? What does that mean? My answer to what that means is this for now. All right? Do you see that? Somebody might say, well, wait, you can't plug 9 in. Well, look, even though f of 9 is undefined, we see this happening. Okay? Even though I can't put 9 in, and we say the limit as x approaches 9, f of x is equal to 6. All right. So that's where we begin. We start off at that point. Now, we'll have to just... once we get this basic idea here, if you're okay with the basic idea, if you can see the pattern, then we just need to look at different examples, and maybe some of the examples are more complicated. The functions are a little bit more sophisticated, but we've got a place to begin with that first example. Okay, so let's look at another function. All right, so look at this one: absolute value x squared minus 9 over x minus 3. And again, I choose this and I say that f of 3 is undefined. In this function, 3 is just not an allowed input. It's not in the domain of the function. But how does the function behave if x is very close to 3? So I'm trying to get you to think about the same question as in my first example. And so I thought, well, let's do it the same way. I'll make a table, and what's the x doing over here? I'm pushing the x closer and closer to 3 from both sides of 3. Okay? And I'm trying to see what happens to the y's and if there's any pattern to the y's. All right? So here I did all the math. You see my numbers on the table. Here, though, I don't think it's like the last one. You know, can you look at this and say that, yes, it's definitive. Every single number is like, are these meeting in the middle, I guess is what I'm trying to say. Is this going to meet that one in the middle? If I was to continue, would they meet in the middle somewhere? Yes. They're going to run into each other at 6 is what it looks like. All right? That's why we're justified in saying the limit is 6. Here, are these meeting in the middle? Like, if you could, like, you could always go closer. 2.999. 3.00004, right? You can always go closer. Are these going to meet in the middle somewhere? It doesn't look like it. This is going off closer and closer to -6. But these are going to 6. Well, -6 is down here. +6, I don't see that they're going to meet in the middle. All right, that's my point. Okay? They're not going to meet in the middle like the other problem. All right. So, well, okay, what's another way of saying that? I can choose x closer and closer to 3. They don't meet in the middle, but we can say, well, it doesn't cause the y to be closer and closer to any one particular number. All right? Well, what do we say in a case like that? We say the limit as x approaches 3 for f of x is DNE. DNE means does not exist, or there isn't an answer, which I guess would be TIA, forget it. DNE means does not exist. So that's what we say. Okay? All right. So now you've seen 2 examples of limits. One of them, we could say, has an answer. And another, we could say, doesn't. Right? Do you see the difference? All right. Okay, so let's go a little bit further. Now, if somebody could say that for me to show you those first few examples, that I am oversimplifying things. I am making them simpler than they actually are. And that's true, but you got to start somewhere. But at some point, we'll have to embrace the full complexity of this. You know, if we're going to learn calculus, that's just the way it is. So the actual mathematical definition is a little more complicated than what I've been telling you. So let's take this first problem that I did, okay? So remember this one, and I made the table, and I said the limit as x approaches 9 for f of x is equal to 6. What does that, oh wait, let me go ahead and, well, let's say it's 3. All right, I messed up there. So let's say there's this function, limit x goes to 9 for f of x is 3. Okay, what does that mean? Like, how would you like give all the details, the full definition? All right, so here's what we got to think. We think about it like this. For the function f of x, y can be made as close as desired, as is desired, to 3 by choosing x suitably close to 9 from either side of 9. You can think of that like there's this cause and effect. Like, really, there's no limit. I mean, what's the closest number you can imagine to 6? I mean, how would you even give an answer to that? 5.99999. I mean, how many 9s do you want? All right? 6.0000004. Like, there's really no conceivable answer to the closest number to 6. So there's like infinite room for me to get close to the 3 if 3 is the limit, okay? So I can get you as close as is desired to 3. You can use your imagination, think I want to be within a nanometer of 3 or something like that, and I can get you there by choosing x suitably close to 9. If I choose the x close enough to 9, I can get you as close as you want to 3. That's how you can think about it. but we've got to look on either side. Notice that on my tables, I chose numbers that gradually push closer and closer to, say, 9 in this example, from both sides. We look on both sides. Not just one side, not just the other side, both sides. So notice I underline from either side. And then the second condition is that what happens at 9, if I say what's the limit as x approaches 9, what happens at x equals 9 is not relevant to the limit. Okay? We don't care about that. If this had anything to do with what happens when x equals 9, we would just say, what happens when x equals 9? That's an arrow, isn't it? It expresses like movement, closer and closer and closer. It's not an equal sign. So for any limit you ever see, x, arrow, whatever, what happens at that spot makes no difference at all to the limit ever, okay? All right. Okay, so we got that. That's kind of a difficult thing for people to accept, but that's the way it is, all right? Okay. And in fact, I'll say once more, when we did this one, and I said that the limit as x approaches 9 of f of x was 6, you can't even plug 9 into that function. It's not in the domain. It doesn't matter. If you're close to 9 for x, you will be close to 6 for y. All right. So now let's try another example now that we've gone a little bit deeper. So see this one, it says, can you evaluate the limit as x goes to 4 f of x, given that the function f of x is, now this is called a piecewise function, okay? Meaning that we calculate y based on whether x is equal to 4 or x is not equal to 4. Y equals 6 minus the x if the x isn't 4. And y equals 5 if the x is 4. Okay, but a function is just x goes in, y comes out. Here's your instructions for getting the y if you plug in the x. Now, I've made some tables in the examples I've done so far. Tables, graphs, it's all the same thing, isn't it? What's on the graph? Points. What's a point? A number x paired with another number y. Whether I give you that in a table or a graph makes no difference. I guess like maybe the precision between them might be different, but it's all the same information. So for this function, I give you a table, I give you a graph. They give us the same information to figure out the limit. Okay? So when I plugged in my x's going to 4, 3.8, 3.9, 3.99, yes, getting closer to 4, very close to 4, 4.3, 4.1, 4.01, yes, getting very close to 4. Then I put them in this one, right? That top one there. How do you get y if you're not plugging in 4? You put it in this formula. Are any of these numbers 4? None of them are 4. They all go in there. 6 minus x. That's how I got all these. All right. Now, so when I drew the full graph, though, I drew the line y equals 6 minus x right here. I know this graph's not perfectly to scale, but it's pretty close. And then I left that open at 4 because on that line we're leaving off the point where x is 4. Well, okay, that would be 4 and 2. Okay, so I'm leaving that off, right? If you did put 4 in here, you would get 2, right? So I gotta leave that open because we're not allowing the 4 as an input right there. But the other part of the definition is if you do plug 4 in for x, you get 5 for y, and that gives me this point, okay? So it's like this second part here displaces this point from there on the line. That's what it is, though. Now, either way, can you tell me what happens as x approaches 4? What's that saying? It says, what happens to this function, to y, if the x gets closer and closer to 4, right? You look at it over here, you say, well, the y will get closer to 2. Are these going to meet in the middle somewhere? They're going to meet in the middle at 2 if you keep going. What about on the graph? Doesn't it say the same information? Like, see this 4.01 right here and 1.99? That's like, I don't know. Where's 4.01? right about there, and it's taking me somewhere over here, a little bit less than 2. Yeah, it says the same thing. And what about 3.99 gives me 2.01? Well, 3.99 is like here, like it's a little bit left of 4, and it gives me some point up here that's slightly above 2, right? I see the graph and the table is entirely consistent with each other. They are the same information. Either way, I can see the closer the x is to 4, the closer the y will be to 2. There's your limit, all right? Whether you get it from the table or the graph. Now, somebody could say, now there's my answer in red right there. That's the limit. Done, calculated. But somebody will say when they're learning this that, well, wait a sec, what about that point? Doesn't that have some bearing on the answer? You know, if you put 4 in for x, you get 5 for y. Doesn't that have something to do with this, or does it mean the answer is 5? F of 4 being 5 has no relevance to the limit. None. Why is that? Because that's x arrow 4. If I wanted to know what happened when x was equal to 4, I would have just said, what happens when x is equal to 4? The arrow expresses this. This is what x arrow 4 looks like. This is what x approaches 4 looks like. All right? Okay. So tables and graphs, all the same information. Let's look at another example. One that is yet a little bit different. So evaluate limit x goes to 3 of 4 over 3 minus x. Now I'd like to take the same approach with the table and the graph. You know, by now you're probably thinking like, you know, when I say x arrow 3, when I say x approaches 3, then this, I hope this kind of thing doesn't surprise you. Okay? You know, I could say, you see that? You know, this is what x approaches 3 looks like. Okay? Now, somebody could argue with my numbers, and I know I haven't mentioned this yet in my other examples, but somebody could say, why didn't you choose 2.6? Why 2.5? Why didn't you choose 2.8? You know, why'd you choose 2.95 and not 2.99? Well, it doesn't matter. I'm just trying to see a pattern, right? Think about it like this. See this first example? Do you really think that you would have come to a different conclusion if that was 8.3 and that was 8.95? I mean, we're just trying to see an overall pattern. It makes no difference, really. It's just that when we try to understand what happens as x approaches 9, for example, then we want to look on a very small scale with the x's approaching 9, okay? We don't want to go 4, 5, 6, 7, 8, 9. No, we want to go like, you know, decimal-wise, very small numbers close to 9, okay? So here, yes, in my table, my numbers vary a little bit. You might wonder, like, why 3.005 this time? Well, look, are these getting closer to 3 is my only real concern, okay? So there, that's what x arrow 3 looks like. That's what x approaches 3 looks like. And that's my key to figuring out what happens within this limit. I did the math over here for y. I got 8, 40, 80 on one side, and I got negative 800, negative 400, negative 10 on the other side. And I definitely don't see these meeting in the middle. So you're probably not surprised I'll say limit as x goes to 3 f of x does not exist. They're not going to meet in the middle, right? Okay, we probably agree with that given the examples I've established so far. I'll go ahead and sketch the graph. It happens to be the graph of something with a vertical asymptote at 3, meaning that this curve approaches that line, never touches it or crosses it in this manner, right? Look at this. Look, if you go to 3 from the left, your y's get bigger and bigger without bound. There's no ceiling to that curve. It just climbs up this vertical asymptote, getting a little bit closer to it, but never touching it, going to infinity, okay? And then on the right-hand side, let's go in this way, 3.4, 3.01. I'm going to go from like -10 to -400 to -800. There's no bottom to this. It goes down to negative infinity. All right? Yes, that's the nature of a vertical asymptote. Now, our initial answer to this question for this limit here is that it doesn't exist. We'll learn a little bit more about this. You might say, well, that's not fair. There's still a pattern here. So we'll learn to say eventually in the future, it'll be real soon anyway, so I might as well tell you now. We'll say, okay, in this table or this graph, here's what we see in a little bit more detail. The limit as x goes to 3 from the left. You see, here's 3, and here's the left of 3. Is infinity. The y's just get bigger without bound. And the limit as x goes to 3 from the right. Okay, so here's 3. Here's the right of 3. The y's get smaller without bound. Negative infinity. So these are called left-hand and right-hand limits. From the left, from the right. 3 from the left, from the right. Okay? All right. Now, so keep this in mind for later. I think it's probably an easy enough concept to understand for now, but there you go. I'll tell you this in addition to just giving you the answer to that initial question. All right? Okay. So let's go yet again a little bit deeper. So I want to give you a function like this and see if you could reduce it to a piecewise function. So what's a piecewise function? We've seen one already in another example. Where was it? I know we've seen it. I've already lost track of my papers. Well, here we go. This is a piecewise function. We calculate the y depending on what the x is. If the x is not 4, we do it one way. If the x is 4, we calculate y another way. Okay? All right. So I wonder, like, can this one be reduced to something like that? You know, maybe this has a really simple way of working where y is this number if x is like that or something like that. So I'll give you two methods to reduce to a piecewise function. First method is what I would think is the easiest way that a person could do this. Let's make a table and see if there's a predictable way of working. Okay? I notice about this function that -5 for x is not in the domain. F of -5 is undefined, in other words. Okay, so I put in some numbers less than -5, and I put in some numbers more than -5. And before I did that, I might just be thinking like, well, maybe there will be a pattern that I'll notice. Okay? So numbers less than -5, more than -5. And then we find out, wait, there's like, how can you miss it? There's definitely a pattern. -2, -2, -2. Everything I put in less than -5 gave me -2 for y. And everything I put in bigger than -5 gave me 2 for y. I would say that's a pattern. I hope you do too. In fact, like I could put more numbers in to try and confirm the pattern, but I'm comfortable saying here's how that function works. Y is -2 if x is less than -5, and y is 2 if x is more than -5. Whoops. Okay. Implied in that definition, given that neither of these say less than or equal to or greater than or equal to, -5 is entirely left out of these instructions, so I could say it's implied in that definition that f of 5 is undefined, just like it is in the original formula. Okay, so this behaves exactly like that would, number for number. All right. Okay, so that's one way that you could do it. Now, another way that you could do it is analytical. It's a little harder, but I should encourage you to learn math as deeply as you can. So let's start off with the rule. The absolute value of a number over that number itself will be 1 if that number is greater than 0, and it will be -1 if that number is less than 0. Okay? If you want some proof of this, put numbers in all day long. It'll confirm what I'm saying right there. Okay? All right, so let's say that that's a rule. We'll just take that for granted. See this thing? I could factor out a 2. And then I see there's a number here and here, and they match, kind of like that. And then maybe I'll factor the 2 out like this and say it's 2 times absolute x plus 5 over x plus 5. Now, how can this rule be applied to that? Well, x plus 5, that's going to be a number, right? That's positive if the x is bigger than negative 5. And it's negative if x is less than negative 5. Oh, so remember this? If number's positive, if number's negative. Also, that would break it down into this. It's 2 times negative 1, being negative 2, if x is less than negative 5. It's 2 times 1, being 2, if x is greater than negative 5. Okay? All right, now, of course, that's the same result. I'd like you to at least consider both methods, but, you know, whatever. I just have to show you and let you do what you want with it, okay? All right, now, let's use this to do something else. Can you evaluate the limit as x goes to negative 5 of f of x, where the function f of x is this? Well, we were just working on that. Remember? F of x, so we just had it. It was negative 2 if x less than negative 5, and it was 2 if x greater than negative 5. Yeah, that was it. Okay. So, what does that... Let's just look at it by the graph. All right? You could look at it by a table too, but let's just look at it by the graph. All right, so here's what I'm thinking. And I'm not going to draw this to scale, so... But let's say that's negative 2 right there. Here's the x-axis, here's the y-axis. So y is negative 2 if x is less than negative 5. So I'm going to put negative 5 like down here. Okay. Since I'm not really, there's no point to drawing this perfectly to scale, so... And then x is... Oh, whoops. I got that all backwards. That's negative 5. And this is 2 and negative 2. Okay, so y is negative 2 if x is less than negative 5, and y is positive 2 if it's greater than negative 5. So it looks like that, okay? And I don't see these meeting in the middle, right? What if we did make a table? Like, and we put numbers slightly bigger than 5 in? They would all give us 2. And suppose we put numbers slightly less than negative 5 in. They'd all give us negative 2. So what I'm thinking is that if I made a table, which I could do if I really wanted to, but if I did, I would see that on either side of negative 5 for x, my y's are not meeting in the middle. Here you're like a solid 2, and there you're a solid negative 2. They're not going to meet in the middle if you make a table. Okay? Now, any time a graph has what we call a jump discontinuity, meaning it's, you know, at 5, it's separated in 2 different pieces, disconnected, then the limit won't exist at that number. Okay? All right. So let's do this. I mean, that's just another way of saying that for my x's going to negative 5, my y's will not meet in the middle. Okay? All right, so we'll say the limit as x approaches negative 5 for the function f of x does not exist. Okay. And then that will be our final statement on that one. All right, but I think it makes it a little easier to understand. We can reduce it as a piecewise function. And no matter how complicated that might look to you, it's just going to either give you 2 or negative 2. All right. Why the open circles? Well, it's undefined at negative 5. There is no y value, so there's no point right there. That's what the open circle means. Okay, all right. So let's do one more for this lesson. Okay, so here I have a piecewise function with 3 different formulas in it. And then I ask you about 2 limits. All right. Okay, so let's see. I will just do these by graphs because I think that's the most succinct way to give you the information. you know, I did mention in another example that, well, you know, the table and the graph is really the same information. But the graph, I think, is a little bit better presentation. So that's just what I'm going to give you for this one. Let me draw the graph of that, and then I'll figure out that limit by looking at the graph. Okay? All right, so how would you graph that? So let's do like this. So it says that y is a constant 4 if x is less than -2. So I'm thinking like, say -2 is right there, and then we'll put 4 up here. Okay, and I'm really not worried if my scale is perfect. Okay, so I'll put this open, and then I'll have a line that goes out that way. And that just says that y is 4 if x is any number less than -2, just like it says there. It doesn't say, according to this first line, that y is 4 if x is -2. So I'd have to leave that open so far. Now from there I pick up with x squared, and I plot that from -2 over to 3. Okay, so where should I start? What should be the very first point that I graph? -2 is not allowed, is it? It says x is greater than -2. I guess I could put -1.99 in and square it and plot that point. But how about this? It just seems easier to say, why don't I put -2 in, and now I'll have to know that that point is open. Okay, so what's -2 squared? It's 4. So I would have to put an open point here at -2, 4. And then I see that this one picks up where that one leaves off. Okay. Now if you had put -1.99 in and you squared it, you'll be somewhere just underneath the 4 right there. I mean, so you'll get a point that's consistent with it, so on. All right, now, so then say I plot the rest of the points, -1, 0, 1, 2, 3. Then I'll end up with this parabola, and like say that's 9, and then I'll get over at 3, I'll get this solid point right there. That's not open, right? Because 3 is included. It says x is less than or equal to 3. 3 is definitely a number suitable for that middle function. Okay, and I'll get 9 if I do that. So I'll get this parabola there with that point open. Okay, and then going up to this point right here. That is 3 for x, 9 for y. Okay, so that's what I got so far. All right, and then 2x plus 1 if x is greater than 3. Oh, how should I do that one? What's the very first point I can put in? Is 3 allowed? 3 is not allowed. It says x is greater than 3. So 3.1? What number should I put in to begin graphing this? Well, just like I was saying up there, let's put 3 in anyway. And then we'll get our value, but we'll know that that has to be an open point since 3 is not actually allowed. It's easier to do that than put some number like 3.1 or 3.01 in that is technically bigger than 3. So take 3. What do we get there? 7. All right. So here's 7 right here, we'll say. And for 3, I'll get this point that's open right there, right under this one. And then the other points are going to be on this line, 2x plus 1, which is a line with a slope of 2 and an intercept of 1. So you could put 4 in, and so you get 9. And it's going to look something like this. Okay, so there's our graph. All right. Open here, closed, and open. Horizontal line, parabola, line with slope 2, intercept 1. All right, so I drew the graph. Now, that's enough information for me to calculate the limit. Now, what's the limit as x goes to -2 f of x? What y's are you going to be getting for x's that are microscopically close to -2 on either side? Imagine if you did make a table and you put in that number right there in red ink that's extremely close to -2. That's going to take you up somewhere really close to 4. And on the other side, this number really close to -2 will take you and give you 4. would you agree that no matter what your choice is close to -2, your y will be close to 4? Okay, so yes, this is 4. That limit is 4. And then what about this one? What happens as x approaches 3? Well, here's 3. If we made a table, some number really close to 3 on the right would give me about, where's this open point? It would give me about 7. And what about some number really close to 3 on the left? It would give me some number like right there, about 9, a little bit less than 9. Are they going to meet in the middle? Well, does the graph meet in the middle, or is it disconnected? Remember, we said if there's a jump discontinuity on a graph, then that limit won't exist at the spot where that discontinuity is. If you made a table, it would, just to revisit the concepts all over again. So I want to make them sink in more and more. If I made a table of this function at 3, it would be like this. The y's would not appear to be meeting in the middle at all. Okay? So what do we say about this limit? Does not exist. There isn't an answer to that one. Okay, so in this we understand a little bit about how to draw the graph of a piecewise function, what it means for a point to be open versus closed, etc. And then once we get that, how to understand various limits from the information on the graph.